Everyone thinks this problem is about swapping, but even with unlimited swaps, you still can't match the arrays?
So what's missing? It's not swaps, it's C-annextions. Once you see this, the answer becomes obvious. Want full solution? Check this video.
Hi everyone and welcome back to the channel. Today we will solve the leetcode problem, minimum homing distance after swap operation. Imagine you are allowed to swap only certain indices in an array, but your goal is to make two arrays as similar as possible. Sound easy? So what if I told you that the swaps form a hidden groups? And the trick is to think in terms of connected groups. In this video, I'll show you how to minimize the homing distance using one of the most powerful data structure, which is union find. So let's dive in. We are given two arrays, source and target, and also a list of allowed swaps. Each swap let us swap elements at two indices. And our goal is to minimize the homing distance. Remember, homing distance is the number of positions where source of I doesn't equal target of I. So let's look at this example. Here we have the source array and the target array and the allowed swaps. And the allowed swaps means that we can swap elements at indices I and j. For example, here is swap 0 and 1 of the source array, or swap indices 2 and 3 of the source array any number of times and in any order. So here the source array can be transformed the following way. We can swap indices 0 and 1, the first indices, so we can swap the element 1 with element 2, and also we can swap indices 2 and 3, so we can swap elements 4 and 3. The homing distance of the source and target is 1 because they only differ in one position, which is at index 3. Because we have 5 here, but we don't have this element in the source array. The key idea here is that if index A can swap with index P, and if index P can swap with index C, let's write it down here. If A can swap with element P and element P can swap with element C, then A and B and C, we can call them all connected. Which means we can rearrange values freely within that group. So instead of thinking about swaps individually, we can group indices into connected groups or sets. And inside each group, we can permute values however we want. To do that, we use the famous algorithm union find. And for every allowed swap from this list, we union the two indices. So we union 0 and 1, and we union 2 and 3 in this example. And at the end, each connected group has a representative root. So let's remember how the union find algorithm works. First, we have two vectors. Let's name it root and rank, which are initialized by the size of either the source or the target. So here the size will be 4 if we work it on this example. So the root is initialized with elements 0, 1, 2, and 3, and so on until we reach the size, and the rank is initialized with the values with the value 1. So all the element here will equal to 1. Then we union each group in the allowed swap. So we union 0 and 1, and we union 2 and 3. As you can see, they all have the same rank, so it doesn't matter which element will be under the other element. So let's say that when the rank is equal, the first element takes the highest rank. So in this case, element at index 1 will be set to the value of index 0, and we will increment the rank here of the first element to 2. The same here, the element or the swap between 2 and index 2 and index 3, and in this case we will give the highest rank to the element 2 because it comes first. So here both elements will have the element 2, and also we will increment the rank of the first element to 2. So this is how the root and rank vectors will look like after we doing the union find algorithm. After that, for each group, we count how many times each value appears in source. Think of it like a frequency map per group. So, for example, if this is our source array and this one is our target array, and the indices 0 and 1 are connected, we can swap 1 and 2. That means that we can swap 1 and 2 freely. So in that group, the source values are 1 and 2. So let's build our groups using this example. We have group 1 and group 2. Group 1, where the indices 0 wins. So first group, let's make it like this. Group 1 will be mapped to the elements 1 that appears only one time, and 2 that also appears in the source array only one. And then we have another group at indices 2, where 3 appears only one, and 4 also repeated only one time. Now we come to the final step, which is we try to match the target values. So for each index, first we find its group, and then we check if target of I exists in that group's frequency map or not. If yes, we use that value or we decrement that value in the frequency map. If no, that means that that element doesn't exist in our map, and that element contributes to our Hamming distance. So let's see this in our example. So we will go through all the indices. So we have index 0 and index 1. Let's copy them and paste. Index 1, index 2, index 3. So at index 0, the target value is, as you can see here, is 2. Target value is 2, and it already exists here in the first group. So we decrement this value to 0. So at index 1, the target value is 1, which also exists. So we will decrement this value also to 0. At index 2, the target value is 4, as you can see here. So we also use it and decrement this value. It's a frequency. And finally, at index 3, the target value is 5 that doesn't exist in the frequency map. So this value is added to the homing distance. So our homing distance is incremented by 1. And as we have go through all the indices, so we return this homing distance value as the final result. So now let's go to the code. First, I have defined the union find algorithm because it's a memorized algorithm, so we don't need to go through it step by step. And we will focus on the implementation of the homing distance. So here first we need to get the size of the either the source or the target array. So we will define a variable n that holds the size. Then we will have or define an instance of the union find class here. Let's name it union find and we give it the size. So the union find here, we have the constructor that initialize the root vector and the rank vector as we have described. The root vector will have incremental variables and the rank variable, the rank array will have all the values set to 1. And the find, as I believe everyone knows, it just check if the that indices, if it doesn't equal its parent, we do a path compression, which is very important here because it minimizes the time complexity. And the union set here that combine every disjoining set into a single set. So here we will define an instance of a union find algorithm and give it the size to initialize the root and the rank. After that, we will do the union of the allowed swaps. So for O2 period in the allowed swap, we will call our union file. I'm naming it here join sets. And I'll give it the pair of 0 and the pair of 1. So till this point, we have created the root and rank arrays, and we have set as shown here. After that, we create our groups, frequency groups. So we will define an ordered map of integer and another and ordered map of integer and integer. Let's name it sets. So for int I equal 0 and I is less than n plus plus I, we will first find the value at index I to get its index. What we need here is to combine the elements based on the group. So we need to reach that element at index 0 equals 0 and elements and equal 1 equals 0, because this form a single group and this form a single group. So first we call the union find dot find based on by index, and then we create the group based on this group or based on this value. So our sets of this group f and a source of I we increment it by 1. After that, we move to the step where we match the target values. So again, we will loop on indices from I to n, from 0 and I less than n plus I. We need here to define an integer called answer to hold the final answer. And we will do the same. We will get the group index, and then we check if sets of f, but at this time we will change the source to target, is greater than 0. That means that the element exists in the frequency map. So if it exists, we will decrement it by 1. Otherwise, we will increment our answer. And at the end, we need to return the answer. So let's run it to make sure that it doesn't have any errors. Oh, yeah, here because we opened the comment, but we didn't close it. So let's run again. And as you can see, all the test cases pass. Let's submit it. And here we go. And that's it for today's problem. As you can see, union find turns a complicated swapping problem into a clean grouping problem. If this helped you understand the problem better, don't forget to like and subscribe. And as always, keep coding with It's a Program with Hossein. Thanks. Bye.